I think that, you guys are playing out the things.
Okay, we're going to continue from where we started on Wednesday, and we're just going to practice through this limit definition of derivative. We'll kind of recap a little bit what we did, and then there's also this alternative limit definition. So we'll do those two. Now, the homework, that's the final thing on the August calendar. I have homework here, which is page 182, 83, which is 2.2. But you can cross off that 55 to 65. You're just going to do 1 through 11 in your packet. 1 through 11 in 2.2, which is page 13 through 16 in your packet. So just AP practice. I'll send out a reminder next Wednesday, just to let you know where the track of 2 pages and where you can find the key, and just as a reminder, homework 2. Okay. So you can cross off 55 to 65 on your calendar. You're just going to do the AP practice. Okay. So page 3. Okay. So we know that our limit definition is basically another notation for slope, right? It's just to find the slope between 2 points that are not locked as specific order pairs, but it has the flexibility to move that h so that when that h decreases, the slope between 2 points will become more and more accurate until it becomes the actual slope at that point of the curve. But we're always going to be adapting our specific function into the slope formula or the limit definition of a derivative, because every graph has its own pattern, its own behavior. So every derivative is going to look different, right? So first thing is, let's go ahead and build our f of x plus h. We know what f of x is. That's going to be just root x. But we have to build f of x plus h. So we have to find a replacement for the x's that we see there. So I'm going to just begin to set that up. And the way we do that is go ahead and leave an empty space where the x was, because we're going to insert something in for that x. And what do you think we're going to put in the space here?
X plus h.
X plus h, right? We're building that point that is a little to the right of our target. Okay. Okay, we can start replacing our numerator. Start inserting into our limit definition. 1 second. Okay, so we have our limit as h approaches 0. I'll write the whole definition out and show the substitution. And again, f prime represents the slope, right? The slope of whatever graph we're looking at. So what can we replace for f of x plus h? Can I replace in place of x? Well, what's f of x plus h equal to? Yeah, square root of x plus h, right? So I can make that replacement. And the reason that we want to do that is because we can't. It's hard to find the limit algebraically when something is in function notation, right? We want to get it out of function notation so that we can actually work with it, whether multiply or add or do any calculations with it. Right? All right, and then what can we replace f of x with?
Square root of x.
Square root of x, yeah. So I'm just color coding it so you can see what I'm going to be putting in this place. So f prime is equal to So I have root x plus h minus, I'm dropping the parentheses around the x plus h because we don't really need it. So minus root x all over h. Okay, so I find that to be the most challenging for some students, where just figuring out how to get started. But now it just becomes a limit problem that we can do algebraically. Okay, what's the first thing that we do for limit problem if we're approaching? Yeah, plug the zero in for what?
The h.
The h. Yeah, so the h is the variable here. Okay, so the h is what's moving. Okay, the x is once we it's going to specify a specific point on the graph, but it's what h is moving here, not x. So replace h with 0. So what's going to happen here? Okay, root x minus root x, which is 0 over 0. So that tells us, okay, that there's a what? There's a hole, which means that the limit does exist, and we're going to continue working for that limit. Okay, but now the limit is going to lead us to some derivative function here. So limit as h approaches 0. What method are we going to be using to help us get rid of that hole?
Conjugate.
Yeah, the conjugate method. Yeah. Okay, so we go ahead and we full the numerator, but we leave the denominator alone. So we multiply that together, we get x plus h minus root x times root x is just x. Denominator, leave what you see, copy everything down the way you see it. Don't try to do anything with the denominator because that h is already sticking out for us to cancel out. Okay, numerator, what can we do with the numerator here? Cancels out, so the x's go away. Now we can do what? Cancel the h's, but there's still a what left over up top, a 1, right? Okay, so a 1. So we have our reduced expression. We should no longer get a 0 over 0. We should now be able to do substitution in for h. So replace h with 0. And what do we get? Yep, 1 over 2 root x, right? Root x plus root x is 2 root x. We add those like terms. So f prime is equal to 1 over 2 root x. Okay, let me talk a little bit about what this means. Now, root x looks like this. Okay, root x is just a radical function. All right. That means if I insert, obviously, if I insert any x value into the original function, it'll give me the y value, right? So if I plug in 1, I get root 1, root 2, root 3, root 4, root 5. But if I plug in any x value from the derivative, it's going to tell me the slope. Now, if you look at these slopes here, these are all very gradual positive slopes, right? They're not very steep. And so what happens is if I plug in 1, 2, 3, these are all values in the denominator. They're all producing fractional slope. So that makes sense, right? It makes sense that we're getting some very gradual, non-steep slopes, and we can see that's what's producing it. And if I try to plug in any negative value, there's no value here. There's no graph here. So if I try plugging in a negative value, it'll give me undefined because I can't put a negative value in for under a radical. So any x value in here will tell us how steep a point is on the original graph. Yeah.
So we don't have to graph it.
No, I just want to kind of give you a visual. I want to convince you that this tells us something a little different about the same graph as y equals root x.
And also, I think I asked this one ago, why is it like f prime of x instead of f of x?
Because so f of x describes the order pair of the function. F prime, we use that notation to represent the rate of change, the derivative of this function. Right. So we want to name it a little differently, because if we call this f of x equals 1 over 2 root x, then we're defining a different function, right? So this is a function that is describing the slope behavior of the original. Okay, so this is So we don't want to think of this as a standalone function. I mean, we can graph it, and later on we're going to graph a derivative function, but right now just know that this is in support of the original function.
The derivative is just like a rate of change.
That's right, rate of change. It's the slope of the original graph. Okay, so let's go back to our part B here. We found the derivative of root x. Part B says write the equation of the tangent line to the function at x equals 2. So that means we want to find the order pair, we want to find the slope, and then put in the point slope form. Okay. So we know that x equals 2 here. How can I find the y value of this function here?
Say you lose 0. Or no. So the x is equal to 2.
Yeah, we'll replace x with 2, right? So what's my y value if I insert 2 into the function? Root 2. So there's my order pair, root 2. And if I want to find the slope, I just insert 2 into the derivative. So if I insert 2 into the derivative, what number am I going to get back in return? 1 over 2 root 2. So that tells us the steepness of this point. So I'm just going to just randomly choose a number here. Let's say 2 root 2 is over here. And ultimately, we're creating the equation of this line, right? We know what the order pair is. We know what the slope is. Now we're going to build this tangent line by putting it into point slope form. So here's our point. There's our slope. It's okay to leave radicals in the denominator. And y minus y sub 1 is equal to m times x minus x sub 1.
So you don't do the h's anymore?
Right, the h's are gone because we took care of it, right? We found a limit, so there's no need for us to involve that h anymore. Okay, so let me now talk about the alternative definition, which will do the same thing as the general definition, but it's going to go down a slightly different process. Okay. So now we're going to find the exact same thing as for example 2. We're still going to arrive at the slope of 1 over 2 root 2 because we're still talking about the same function. We're still asking about the slope at the same point, but we're going to use a slightly different definition. So I'm going to introduce this alternative definition of a derivative and kind of talk about what's different about it. So I'm going to put that definition right here so we can kind of see how we're going to change and adapt and fill it in. Now, if you look at this this alternative limit definition, it feels a little bit different, right? Instead of h approaching 0, it's x approaching c. But the nice thing about this alternative definition is that it's easier to see that slope field, right? Change in y over change in x. It does have that more of a kind of a slope feature to it, more so than the limit definition, because the denominator kind of dropped out. So, but we knew that this came from slope. Okay, but this looks more like slope, right? Change in y over change in x. Okay, so the first thing we do is we're going to replace all the c value with the numeric value that we're concerned with. Okay, so everywhere you see that letter, we're going to go ahead and replace with 2. So that's the first thing. Once you do that, things will become more clear as to what we want to do for this problem. So we want to find f prime of 2. So we're going to get the same goal as above. We should get the same answer, but we're just going down a slightly different process, okay? Limit as x approaches what? 2. F of x minus f of 2 over x minus 2. Now, this is still a limit problem. We still want to go through and do direct substitution, but we first want to get the numerator out of function notation. So What do you think I can replace f of x with? Square root of x, right? Square root of x, okay. Now, f of 2, what does that mean? Or how can I evaluate this to get it down to get it out of function notation? Yeah, put 2 in the original function. That's what f of 2 is. So what's f of 2 equal to? Okay, so f of 2 equals root 2. So I'm going to replace f of 2 with root 2, and I'll put it here. So it's similar to the general definition in the sense that we want to just get the numerator out of function notation, right? Get it out of function notation so we can actually do the steps that we know with limits, which is direct substitution. So what's next? Well, before that, we're going to confirm what? Yeah, plug 2 in and we get 0 or 0. So again, we know there's a hole. So yep. So again, conjugate method, because you see radicals involved. So multiply the top and bottom by what? Root 2. Good. Foil the numerator, but don't do anything to the denominator. Just copy what you see. Okay. What do we get from the numerator if I foil this out? X minus 2. All right, what do you see here?
Two like terms.
Guess us out. What we're left with?
1 over square x plus.
So now that the hole is gone, what can we do? Substitute the x with 2. So with limit definition, the general definition, you're replacing your h's with 0. Here, you're replacing x with 2. Okay, so what do we get? 1 over
Root 2
root 2 plus root 2. Yep, which is 2 root 2. Okay, do we get the same answer as above? All right. But here's what's different. The difference is that your limit definition will first take you to a formula, and then you can take a second step to get to the slope value at that point. But the alternate definition will take you directly to the slope value. It will bypass the slope formula, and it'll just take you down to a number. Okay. So I think a general definition is more it's more usable, because once you get to the derivative function, you can reuse it for other points. But this one, if I want to find the slope at a different point, I got to restart the process and begin again.
When you like different like strategies,
Yeah. Now,
it's like, oh, you need to like learn how to do it both ways.
right. So the purpose of this is twofold. The first is for us to recognize that derivative is very much connected to slope, right? We see that slope feature involved at the beginning of our formula, and just to understand that that the derivative function comes from a slope formula. Okay, so that's the first one. And the second is on the AP exam, typically they don't ask you to work a problem from scratch, saying, hey, what is, because we're gonna have a much more efficient way to get to this process. We're not gonna have to go through all this. But what the AP exam can do, what it can do is that it can show a problem halfway and ask you, okay, what does this mean? They can say, okay, so what is this asking for? Right, and we need to be able to look at this and say, okay, this is asking for the slope of a function at a point. And if the function is showing as root x minus 2, or this right here. So if we were to see this, what does this mean? This is basically saying, okay, this is asking for the slope of a function of root x at x equals 2. Right? Can we look at this and realize that it's coming from, it's asking about the derivative of f of x for this function, right? And that's the That's what's more important, to be able to kind of understand what it's asking for rather than, doing the whole process from beginning to end.
We'll have more practice with this.
Yeah. So we're going to do that more practice right now. Yeah. Okay. That's what we're going to doing. That's what we'll be doing for today. But I want to just talk about some definitions or vocabulary here for a little bit. The word differentiability. It comes from the word differentiable. So in order for a function to be differentiable, understand that that word means a smooth curve. Okay? That means a slope will exist at every point on the curve. Okay. Then the graph must be continuous at that point. It cannot contain a sharp turn. It cannot have a vertical tangent at that point. So this would be an example of a function that's differentiable, where at every point you can imagine there to be a real number slope value at that point. Okay. So what are graphs that are not differentiable? Graphs that are not differentiable will be graphs that have a sharp turn or a sharp corner. We cannot create a slope of a tangent line at a sharp turn. So this would be a graph where this point has a slope that is undefined. Okay, slope is undefined here. And obviously a slope is also undefined if it's at an endpoint. Okay, or if there's a jump, right? We cannot find the slope at an endpoint. So if there's not continuous, if there's a hole or jump discontinuity, we cannot find the slope at that point. So we call that it is not differentiable here as well. And then finally, sometimes you have graphs that look like this. I'll draw it again, where there's like what we call this a vertical tangent line, where you can draw a tangent line, but the tangent line is going to be vertical, and we know that the slope of a vertical line is undefined. So this would be a continuous function, but the slope would be undefined because the slope of a vertical line is undefined. So these are three places where we say a function is not differentiable because the slope is not defined at these points. So I can write this way here: f prime of a does not exist here. F prime of a does not exist here, and f prime of a does not exist.
Also, it's not undefined, it's defined.
Same thing, DNE and undefined. I'm going to use those interchangeably. Okay, so we'll do some more practice here. Let's go to the back page 4. Okay, so let's do let's skip number 1 here. Let's do number 2. Let's do the general definition for number 2. So my f of x, I wrote it as y, but I can just easily say f of x equals 5x squared minus x. So the challenge is always how do we get that f of x plus h to show up? So I like to do this. Go ahead and replace every x you see with a set of parentheses so that you are creating a reserve spot for your x plus h.
You recommend doing that for like every problem? See,
Yeah,
you recommend doing that for every problem?
yeah. Otherwise, I feel like students may put an x plus h in the wrong place. I see some students, they will do 5x squared minus x, and they'll just put a plus h at the end. But the x plus h is going to have to go in these spots. And if we can do that, then we're not going to make a mistake, right? Okay, so what's next? Where can I put the x plus h?
F of x plus h equals
Mm-hmm.
5x plus h squared minus x plus h.
Yeah, so once you have those reserve spots, you know that is where your x plus h is going to go.
Why is there a square root in the last one then?
There's a square root in the last one because the function is defined with the square root, right? So we're always going to have to follow whatever the function looks like, right? Because if we don't follow what the function looks like, then we're not creating a slope formula for that function. Right? We have to be able to have something to work off of, because we're building a slope formula for this particular function. So the features need to be from that original function. Okay, so now f prime equals Okay, what comes first? F of x plus h gets replaced with
5x.
yeah, this whole thing, right? Right? All that gets put in place for that first portion of my numerator. But we're not done yet, right? What comes after that? What comes after this?
The f of x.
Yep. And what's f of x? Good. Now, there's something that we have to be careful about. What do we be careful about when we put this 5x squared minus x in for this f of x? Okay, why do we need to have a set of parentheses or brackets here?
Differentiate.
This negative here. This negative is going to cause an issue if you don't have a set of parentheses. Otherwise, you're going to forget to distribute, and that's going to throw off your sign, right? So you want to do minus big parentheses. If you don't have this parentheses here, you're going to keep this negative as a negative. It should, eventually turn out to be a positive. Okay, all over
H.
Okay, so now this becomes a limit problem, right? The hardest part is just setting it up. After this, you're just plugging in 0 in for h, and I'll get 5x squared minus x minus 5x squared plus x. What do I get here? 0 over 0. So you know that there's a hole, there's an h hiding in the numerator. So we're going to fool everything out, clean everything up, factor the h out, cancel out, and reevaluate.
How you get zeroed up because like you can't plug in anything for x.
Remember, it's not x that we're replacing. We're replacing h's with 0.
So you just ignore the x's.
Well, we don't ignore the x. The x is, imagine x as a value that's not changing. Okay, so let's do this. If I replace 0 in for h, what do I get? I get 5x squared. That cancels out with this 5x squared. Right. If I plug in 0 in for h, negative x plus x, that's 0 as well. So everything cancels out. I'm just left with a 0. Right. Okay, so let's FOIL everything out. Now we gotta be careful with this. I'm skipping a step here. Really, we should be writing that x plus h twice, right? We don't want to say, oh, that's just x squared plus h squared. It's x plus h times x plus h. And I'm just combining the middle terms there. Okay. Continue cleaning up. You can probably drop I can distribute the 5 through and I can drop the parentheses. Okay, what can we clean up here? X's can go. What else can go?
5.
What else cancels
Oh,
out?
the h's.
Not yet. Yeah, maybe 5x squared minus 5x squared, that goes away, right? So now we're left with no more like terms, but what can we do with the numerator? We can factor out a what? H, yep.
You have to keep writing like limit every single time you go down.
Yeah, technically we should be doing that. Okay, so h comes out. We're left with 10x plus what? If I factor in h out of
Plus
this,
5 squared.
plus 5h,
5/8.
yeah. What happens here? What if I factor an h out of this?
Minus-
Just 1. That's right. There's still a 1 left over. It doesn't completely go away. Still have a 1 for that term. Okay, do you see what's causing the hole here?
Yeah.
Cancel the h's out. So now, final step, replace what? H's with 0. So what are we left with? 10x minus 1, because the 5 times 0 is just 0. So here's my slope function, my derivative function. This is built specifically for this 5x squared minus x, right? Every function is going to have a different pattern. So that's why every derivative is going to look a little different, right? Every derivative is describing a different function. So any point I plug in here will tell me the slope of any point on this graph.
You always get a variable in the answer, right? You'll never be like,
Unless it is a linear graph. If it's a linear graph, then your slope would just be a constant. Because like 5x plus 2, same slope all the way through, so you're going to just get a constant. But yeah, if there's any curve involved in the graph, you're always going to get a variable, because you want to create a formula that is adjusting to every change on the curve, right? Okay, let's look at number 4. So now we're dealing with some fractions here. Okay, first things first, we're going to use this limit definition again. We want to build our f of x plus h, but let's go ahead and put our parentheses in place so that we don't put them in the wrong place.
f of x plus h equals 1 divided by x plus h minus 2.
Good.
We're kind of putting parentheses over like that x plus h is right.
Initially, yeah, initially, so that you don't put the x plus h in the wrong place. But then once you have it and you're ready to clean up, you can start dropping it. Yeah. But if you don't have the parentheses there, though, I think it's easier for you to not know where to put it, or to maybe place it in the wrong spot. Okay, so limit as h approaches 0. Right, we need to find a suitable replacement for f of x plus h, and we've created that, right? So 1 over x plus h minus 2. I can drop the parentheses because there's nothing outside the parentheses that's changing it. So minus what? 1 over x minus 2. Yeah. All over h. All over h.
This is common denominator.
This common denominator problem. Okay, so
We're
first
putting
thing,
0 first. Yeah.
yeah, so plug in 0 first. We get 1 over x minus 2 minus 1 over x minus 2. They're the same. I get 0 over 0. So we got to work on this portion here. We got to get that common denominator. What is our common denominator?
X plus h minus 2 times x minus 2.
Good. So we need both of them, right? Even though they look like they're kind of similar, they are completely separate from each other. So both denominators need to be part of my common denominator. Okay, so we need to balance our fractions here. Looks like the first denominator is missing the x minus 2. So I need to balance the top with the x minus 2. So x minus 2 times 1 is just x minus 2. This denominator is missing the larger x plus h minus 2. So I need to multiply the top by x plus h minus 2.
So you included -2 in the parentheses now?
I do, yeah. Why do I want to have this in a set of parentheses,
So
but not this one?
differentiates. Helps cancel out.
Something else, something that I'm afraid of forgetting to do if that negative, right? If I leave the parentheses out, I may forget to distribute that negative through each of those terms. Okay, so now I'm going to combine these fractions together. X minus 2 minus x minus h plus 2. Okay, so I haven't brought in the divided by h yet. I'm just trying to clean up this numerator portion. Okay, so I think this next step I can do it now. Limit as h approaches 0. What cleans up in the numerator here?
The twos and the
Yeah,
X.
good. The 2's and x's, all I'm left with is what?
H, negative H.
Negative h. Okay, so I have negative h over x plus h minus 2. Okay, now I'm going to bring back the original h from the very beginning of the problem, divided by h. Okay, so I still have a complex fraction, but it's a little bit cleaner now. Now I can just bring that h up as the reciprocal. So times 1 of h, and I should then get the h's to cancel out from it.
You said he's -1 there.
We do, yeah. Oops. Okay, so do we spot the hole here? H, yeah, but we're gonna keep that -1. Okay, final step
Plug in 0
for
for h.
h. Okay, so 0 goes in here. What am I left with? X
X
minus 2. Okay, so x minus 2, x minus 2. Yep, so you're right. I can merge that together and make it x minus 2 squared. So here's my derivative. F prime is equal to -1 over x minus 2 squared. So this is the slope formula built specifically for this original 1 over x minus 2. So whatever this graph looks like, any x value you plug in, any number that you find here is describing how steep the original graph is.
Also, you never like foil the bonds? You just keep-
We don't, yeah, so I think we prefer factored form. Factored form is cleaner. You can find more information that way, so it's not wrong if you fold it out. It's just, it's more useful in factored form, especially for down the road when we're looking for certain properties. It's easier to find things in factored form. Okay, let's keep going here. Next page.
What does the H stand for again?
The H stands for the fact that that normally slope requires 2 points, but if I can somehow move those 2 points and move it into the same point, then my slope it becomes much more accurate, right? And that H allows me to basically use slope using 1 point because that H is eventually moving those 2 points into 1. So it basically allows me to adapt the slope formula so that the accuracy is exact and not just an approximation. Yeah, so the H basically allows us to merge slope requiring 2 points into slope only requiring 1 point because we're moving the second point into the first one. Okay, so page 5, let's try the alternate definition. Wait, did we do this similar one to this already?
We did it like on the back. We did an example of it.
Similar to it, right?
Page 3.
Okay, let's go to page 6 then. Why don't we do the alternate definition for number 4? Okay, I'll put the alternate definition right here. It says use limit definition, but just for practice purposes, we'll do the alternate definition. So here's the alternate definition: f prime of c .
Way to memorize this formulas.
I'll probably give these to you. Yeah. What's the okay? So what's the first thing that we did when we did the last problem?
Means parentheses.
Yeah. Well, this is the alternate definition here.
Change the speed.
Yeah. Replace all the c's with what?
3.
3. Okay. It'll make things more yeah, more specific to the problem, right? I think that's a good first step because things will become more clear what we're trying to achieve. So now we have a better idea as to what to replace, right? We're always replacing the numerator. So what can I replace f of x with?
2.
Yep, 2 over 5 minus x. And how can I find f of 3?
Plug it into.
To the original. Good. All right. So I'll put that over here. F of 3 equals 2 over 5 minus 3, which is equal to what? 1. 2 over 2 is 1. Okay, so my numerator will be replaced, and then once I get those replaced, I can just treat it like a normal limit problem. We still have to deal with this complex fraction potentially. Now I'm going to put a 1 over 1 here as a reminder that we're going to have to find a common denominator. Everybody good so far? Okay, so I'm going to box this off because this is what I'm focused on. What's my common denominator? I'm just going to work on that portion right there.
5.
5x times 1.
Well, just 5 minus x, right? 5 minus x. Now the 1 is basically just is not going, time. It's basically 5 minus x times 1, but we know that times 1 is just going to kind of go away. So my common denominator is just 5 minus x. Any changes between the old denominator and the new denominator here?
5 minus x is still no.
No changes. So the 2 will just stay as 2, right? Just times 1. Okay, any changes here?
5 minus x is numerator.
Yeah. Now, what should I do with this 5 minus x?
Make it 1. And they divide it.
Something I should put. We should put what around this parentheses because, yeah, that negative, right? If you don't, it's going to potentially mess with us. Okay, so here's my cleaned up version: 2 minus 5 plus x all over 5 minus x. This cleans up to be -3 plus x over 5 minus x. Okay, so this is, I'm just stepping away from the problem a little bit. I'm just trying to get that numerator cleaned up. So now that I have my numerator cleaned up, I'll put this back into my problem, and I should be able to get things to work. Yes.
Why can't you just cancel out the 5s and the x's and just have
What I was going to ask you.
Cancel these out.
Yeah, like -1.
no,
Okay.
on the other side. Like 2 minus 5.
Uh-huh.
Just cancel those out and leave the 2 and then.
Okay, so yeah, so we cannot cancel across addition and subtraction. Now, if it was 2 times 5 minus x divided by 5 minus x, then it's fair game. But anytime there's addition and subtraction, we gotta be careful. We cannot cancel it out. Yeah.
I was gonna ask like like when we had just 2 different denominators before we combined them.
Right.
Why can't you just divide 5 minus x divided by 5 minus x?
So right. So if we cancel the 5 minus x out, then we're back to where we started, and we don't have common denominators anymore. So the whole point is we want common denominators so that we can actually merge the numerators together. Otherwise, if we're subtracting 1, we're back to where we started. Okay, so now let's go back to my original problem. So this piece is now in place of that. All over x minus 3. Okay, so we're beginning to see some similarities, right? If I multiply by the reciprocal of this, that should do something with that numerator there. So let's get that to show up. Dividing by x minus 3 is same thing as multiplying by the reciprocal.
This makes it -1.
Times 1 over x minus 3, right? Now, yeah, these are in different order, but these are the exact same, right? The x is positive, the -3 is negative. So the order is different, but this we can cancel out cleanly.
Oh, the whole thing.
The numerator, and yeah, because that's all one thing, right? They're not being attached to any other addition and subtraction. Okay, so this should take us to our slope here. F prime of 3 equals, replace 3 in for the remaining x, 1 over 2. So this takes us directly to the slope. So the alternative definition doesn't take us to a slope formula. It takes us to the exact slope at this specific point.
So it'd be a linear.
Huh?
It'd be linear.
Well, this is the slope. So the graph may look something like this, but it's just telling us the slope at that point. So the graph is still a curve, but obviously the slope is just going to be a number. Okay, come get your phones. I'll send out a reminder next Wednesday about the assignment that's due.
We can apply like unit circle to stuff like this. It'd be like
Unit circle won't come until like November.
okay. Will we have to apply a derivative though?
Yeah, we're going to applying derivative to trig functions.
Oh,
yeah.
We can get test graded.
Hoping next Friday, we'll see. Okay, great, thank you.
Oh, they just had some bad lunch yesterday. You just don't different. Took me the whole class. Like, I was still gonna find like 20 minutes to even have to.
Yeah, when it's the tower.
I don't think that.
Everybody's saying that. So I don't work.
You're saying you're drafting your baseball team yet?
I got another draft coming up next week.
Dropping in Bill's what if you?
James Cook is on.
Oh, yeah.
Right?
Oh, he's gonna like good choice. He's gonna break out this year.
You think so?
Yeah, he's a very undervalued pick.
Well, the problem is that Josh Allen, he basically is the running back. So
No, but like they're gonna put more emphasis on him like hitting it off, I think.
you think so?
Yeah.